In this video, I'll go through the answers for the Chapter 14 worksheet for OpenStack's 10th edition organic chemistry. So our first question is about the conjugated pi bonds and butadiene. And so let's look at that. So butadiene has two conjugated pi bonds. Draw a bond line structure for butadiene. How many electrons are in the pi system of butadiene? So if we draw a bond line structure for butadiene, and sometimes you'll see this written 1,3 butadiene, but in the case of butadiene, it's unnecessary to give the locants for the double bonds because there's nowhere else to put them. You can't have a diene and butadiene without them being at the 1 and 3 positions. But if it were pentadiene, then you would need to indicate where the double bonds are. Anyway, that's a bond line structure. How many pi electrons are in the pi system for butadiene? There's 2 here and 2 here, a total of 4 pi electrons. Okay, the next question on the worksheet is question 2, which is sketch a molecular orbital diagram or MO diagram for butadiene and label the bonding and antibonding orbitals. Check your work against figure 14.3 in the text. And so if we come to here to this drawing tool and do that. All right, so we want to do an MO diagram for butadiene. That's the goal. And so in order to do an MO diagram for butadiene, we know it's a conjugated system, and the conjugated system contains 4 pi electrons. And so they're going to be 4 electrons in 4 different p orbitals spread throughout this molecule. So spread throughout this molecule right here. 1 electron here, 1 electron here, 1 electron here, 1 electron here. These are sp2 hybridized atoms. The pi bonds are being made with the unhybridized p orbitals. These are all the p orbitals representing the electrons in those orbitals. So an MO diagram, molecular orbital diagram, you draw your energy axis, and you're going to have 1 orbital go down, 1 orbital go up, 1 orbital go down, 1 orbital go up, and that's it. There'll be 4 orbitals, 4 molecular orbitals. That's what we're drawing over here, because there were 4 atomic orbitals. The number of molecular orbitals will equal the number of atomic orbitals when you combine atomic orbitals into a molecule. Now, anything that is below this line energetically is considered to be bonding. Anything that is above this line energetically is considered to be anti-bonding. So these are anti-bonding, and these are bonding. If you look at these electrons in these individual orbitals and ask the question, where would they go into our molecular orbital diagram? We have 4 electrons. We're going to start off by putting them into the lowest energy orbital. We're only allowed to put 2 electrons in a given orbital, so then we have to go up. And now we've run out of electrons. So all 4 of these electrons go down in energy. They all go into bonding orbitals as a result of this conjugated system, as a result of these molecular orbitals. Now, you can also sketch the orbitals themselves. And so this is the diagram that it's referring you to. So these are our 4 isolated p orbitals. You can sketch them as the 2 lobes. And the lowest energy lobe is going to have the lowest energy molecular orbital is going to have all of the lobes in phase with no nodes, no breaks in their connectivity of phases. The next bonding orbital energetically is going to have 1 node. So as you go up in energy, you're increasing the number of nodes. So we're bonding here, no bond here, bonding here. And that looks a lot like our representation of butadiene from our bond line formula. Pi bond here, no pi bond here, pi bond here. And then we have these anti-bonding orbitals, which we're not currently using because we only have 4 electrons. So this is one way to draw it if you want to show all the lobes. This is also an energy diagram for the for butadiene. Sorry, I'm kind of distracted here. All right, let's move on to question 3. The next question from the worksheet is, using your MO diagram above, how many nodes are present in each pi orbital of butadiene, how many nodes in the HOMO, how many nodes in the LUMO. And so we kind of already did that. In order to get the nodes, you would have to draw out the orbitals. So I'll just go ahead and refer to what's in the text here. In order to see how many nodes there are, there's 0 nodes in the lowest energy orbital, 1 in the next, 2 in the next, and then 3 in the highest energy orbital. And the next question was how many nodes in the HOMO and the LUMO? And so that means identifying the HOMO and the LUMO. The HOMO is the highest occupied molecular orbital. So this is your HOMO, highest occupied molecular orbital. This is your LUMO, lowest unoccupied molecular orbital. The energetic gap between these two, this difference in energy, is called the HOMO-LUMO gap. And that's what we observe, or what we detect when we do UV spectroscopy, which we'll talk a little bit more later in this chapter. So this HOMO-LUMO gap, energetically speaking, ends up being useful for characterizing molecules. If you're working with a semiconductor material like a solar cell, the size of that band gap, or that HOMO-LUMO gap, has a big effect on the properties of the material. Question 4 is about isolated, conjugated, and accumulated double bonds, and then some other questions about HOMO-LUMO gap and lambda max. So isolated, conjugated, and accumulated double bonds. So for this problem, I'm going to say isolated, I'll circle in red. Conjugated, I will circle in purple. And then accumulated, I will circle in black. So any accumulated double bonds here? Yes, here are some accumulated double bonds. Nowhere else. Remember, accumulated are the sort of the weird ones. What about conjugated? We need double bonds that are conjugated. Well, here, all 4 of these are conjugated. You have alternating double bond, single bond, double bond, single bond, double bond, single bond, double bond. That means you have a conjugated system. All of these are conjugated, but the one on the end over here is not. It is actually isolated. It's isolated because of this carbon atom right here. It's an sp3 hybridized carbon atom. And so because of that, it sort of blocks the conjugation and isolates that one double bond. Because there's no p orbital here in this carbon atom, there's no way for the electrons in these other p orbitals to have that continuous network. So getting back to the problem at hand, what's going on over here? This is isolated, and this is isolated. All of those are isolated. These 2 are isolated. These 2 are isolated. And then all of these are conjugated. So all 3 of these are conjugated. Which of the first 2 compounds is more stable? Well, remember that more stable molecules are going to be lower in energy. And we learned that the conjugation decreases the energy of the system. So the more stable compound is this one. Less stable is the one with a less conjugation length. Which of the first 2 molecules or compounds has a higher lambda max, and which has a larger energy between the HOMO and LUMO, or larger HOMO-LUMO gap? And so those are really related, but they're not exactly the same thing, but they are related. So let's talk about the HOMO-LUMO gap first. So if you just have, this is ethene or ethylene. So we're just having a conversation over here about, here I'm talking about ethene, or any molecule, longer molecule with just 1 pi bond. So you have these 2 p orbitals. They're going to combine into a HOMO and a LUMO. So this is your HOMO, this is your LUMO, and you see we go downhill in energy. If we compare that with butadiene, well, butadiene is going to have, so here's another energy axis. Same energy as relative to the one on the left should be the same scale. So this has 4 p orbitals, and 1 down, 1 up, 1 down, 1 up. And what ends up happening as you add more and more orbitals to this, the HOMO and LUMO, all the orbitals, become closer together. So your HOMO and your LUMO end up being closer together. No, I'm not sure how well I represented that here. What I'm saying is this gap here is smaller than this gap here. And so as you add more and more and more, so you can imagine a molecule that has a whole bunch of pi bonds. So it would have 8 p orbitals, all filled with electrons. And so you have 1, 2, 3, 4, 5, 6, 7, 8. We're going to fill up the bottom ones. 2, 4, 6, 8 pi electrons. 2, 4, 6, 8. We're below the bonding line. And this is our HOMO, and this is our LUMO. And so the HOMO-LUMO gap gets smaller and smaller as you add longer conjugation. So increasing conjugation length decreases the energy of the HOMO-LUMO gap. So which of the first two molecules has a larger energy between the HOMO and LUMO, a larger HOMO-LUMO gap? This molecule has the larger HOMO-LUMO gap. So larger energy between HOMO and LUMO, it's this one, not the one on the left, because it has a smaller conjugation length or a shorter conjugation length. Finally, which of the first two compounds has a higher lambda max? So lambda max refers to UV vis spectroscopy. So in UV vis spectroscopy, you'll get plots that look something like this. You have your absorbance, you have your wavelength, and then we're looking for some big peak in the absorbance. And we look at this wavelength, that's your lambda max. And lambda max is closely related to this HOMO-LUMO gap because wavelength is proportional to energy. Well, it's inversely proportional to energy. And so as the energy difference between the HOMO and the LUMO changes, the energy required to excite an electron changes. Absorbance is the absorbance of electrons. It's exciting an electron, or excuse me, absorbance of photon that is exciting an electron from the HOMO to the LUMO. And so a larger HOMO-LUMO gap actually ends up in a lower lambda max, and a smaller HOMO-LUMO gap ends up in a larger lambda max. And so if you remember, we had this equation, E is equal to hc over lambda. So energy and wavelength are inversely proportional. The other two, they're constants. The other two symbols there are constants. So energy and wavelength are inversely proportional. As this energy difference becomes larger, wavelength becomes smaller. So you end up with lower wavelength of absorbance. As this energy difference becomes smaller, or the HOMO-LUMO gap becomes smaller, your lambda max becomes larger. And so what that means is for molecules that don't have much conjugation, they're going to absorb more on the left side of this plot. For molecules that have increased conjugation, they'll absorb more to the right. And it turns out that most organic molecules that have any conjugation, they kind of absorb back here to the left of what we call the visible spectrum. So the visible spectrum is around 400 to 700 nanometers, plus or minus a bit. And so it just turns out that most organic compounds don't have color, but as you get to larger and larger molecules, longer and longer molecules, then you start to see a smaller HOMO-LUMO gap, and therefore a higher lambda max, and that allows you to see color. I'm looking for like a beta carotene or something. There it is. So you can see these molecules like beta carotene have this really long conjugation length. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 double bonds are all conjugated. And so this is beta carotene's UV vis spectrum. And you can see that the lambda max is at 455 nanometers. So that will absorb visible light, which means our eyes will detect a color. If this lambda max goes to the left and leaves the visible range from 400 to 700 or so, then we will lose that color. And that happens as that HOMO-LUMO gap gets larger. Again, one last time, larger HOMO-LUMO gap, larger energy, smaller lambda max, smaller energy between the HOMO and LUMO gap, larger lambda max. All right, so question 5 from the worksheet. Is predict the major product of each reaction below. Identify major or minor products if more than one product is expected, including stereochemistry. Write a mechanism leading to the formation of each product and label the kinetic and thermodynamic products if they differ, as in butadiene. All right. And so when you're working through these, I don't really expect you to rigorously do every single one of these. You have to use your judgment. You have to manage your time. You're working all the problems from the book. You are looking at the practice exam and working that. And we're covering what we cover in class. This is an extra layer. This worksheet is an extra layer. So I would definitely recommend working through these. But once you see the mechanism for one and you realize they all have the same mechanism up to a point, then you probably don't need to show the mechanism for each of them. But let me get into the details. I think that'll become more clear. So for the first one, we're going to do it all. We're going to start off. So I'm looking at this one, this first one at the top left. So I have this alkene plus HCl. And remember that this is just electrophilic addition of HCl to an alkene. So this is going to form a carbocation intermediate and chloride. Now, if you want to be really careful, you can keep track of all those hydrogen atoms that were already there, plus your new hydrogen atom that you just added. It does not matter if you put the positive charge on the top here or the bottom, just so long as the positive charge goes with the carbon atom that only has one hydrogen attached and not two. So now we have this carbocation, a very strong electrophile. We have chloride in solution, a good nucleophile. And so we're able to move the reaction forward to form this product. And again, if you wanted to be really careful, you could show all the hydrogen atoms wherever any bonds were made or broken in the reaction. It's not a bad habit. So that's our final product. Our final product is this. And so if we add HCl to a different alkene, one that has an extra methyl group here. So I'm just going to come over here and get rid of that. You know what? Let's not do it that way. Let's just do it one more time all the way through. So if we have this alkene and we have HCl, then we know that we could attack this proton to get a carbocation. And our choices are to form the carbocation at the tertiary carbon or at the secondary carbon. And we know that the secondary carbon is not going to form the carbocation, the tertiary carbon is going to. So then we can take our chloride, acting as a nucleophile, and attack our carbocation to give this product. And this is what we call Markovnikov addition of HCl across a double bond. The H and the Cl were added across a double bond. There's an extra hydrogen here and a Cl added up here. And Markovnikov addition states that the hydrogen is going to be added to the less substituted carbon. The chlorine or the halogen will be added to the more substituted carbon atom. This is true when you have this carbocation mechanism. So both of these went through a carbocation mechanism, and they got very similar products. HBr reacts a lot like HCl. You're going to form the secondary carbocation, not the primary carbocation, to get this product. And the same thing for this alkene. You'll get the tertiary carbocation, not the, let's get rid of all that, not the primary carbocation, which were the two options. Why can't I hit that right? Yeah. And so as you work through the mechanism, you'll find that for this one, you would had a choice between putting the positive charge on a tertiary carbon or a primary carbon. Up here, the choice was between a secondary carbon and a primary carbon. Now, HBr and peroxide is a little weird because in this case, you're actually going to get anti-Markovnikov addition. Anti-Markovnikov addition of H and Br across the double bond. And so if we remember, that's a radical mechanism. Depending on who you took the course with, you may or may not have seen the mechanism yet, but we definitely learned about anti-Markovnikov addition of HBr in the presence of peroxides. And that's the key difference. No peroxides, you get Markovnikov addition. With peroxides, you get anti-Markovnikov addition. This only works for HBr, nothing else. So addition of HBr to an alkene. That ends up being very useful synthetically because if you have a double bond and you want to activate the central carbon only, you would do this reaction. If you had a double bond and you wanted to make it so that only the terminal carbon was active, you would do this reaction. That mechanism, remember that H2O2 is just this. It has that weird OO bond, which is very susceptible to breaking. You form two radicals. The radicals can then react with bromine, with HBr in solution to give you water plus a bromine radical. This bromine radical can then attack the double bond. So this is addition of a radical to a pi bond. And so we do this and this and this. Notice I'm choosing to put the radical onto the tertiary carbon, not the primary carbon, because remember radicals are electron deficient species. So just like carbocations, they want to be on the more substituted carbon atoms. And so in this case, with the addition of radicals, a radical source, peroxides, we're not adding the hydrogen to the alkene first. We're adding the bromine to the alkene first. And that's why you get this anti-Markovnikov addition. The bromine goes to the terminal carbon so that you can form the more stable intermediate. Similarly, in this case, hydrogen went to the less substituted carbon so that you'd form the more stable intermediate. So the logic is the same, it's just a different mechanism. Without peroxides, you go through a carbocation mechanism. With peroxides, you get a radical mechanism. Finally, once you have this radical, you can generate more bromine radicals in solution. Remember that radical mechanisms are chain mechanisms, so you wouldn't want to take this hydrogen from peroxide or something else. Instead, it's better to show it coming from HBr because now you have a system where it just continues to propagate without the need for more radicals being added. Okay, and so this is our product, which is shown up here. If we had one equivalent of HBr to butadiene, we expect to get both 1,2 addition and 1,4 addition. So you remember we get 1,2 and we get 1,4 addition. Under cold conditions, we're going to preferentially get the 1,2 addition more so than the 1,4. So this will be the minor. And X isn't quite right here. It's more like just saying minor. And the major product is the one circled. And so why is that? It's the same reason as before. It's Markovnikov addition across a double bond. So you have a double bond. That's going to form the more stable carbocation, the allylic carbocation, not the primary carbocation. That was the other option. And then, of course, this has two resonance structures. And we learned that 1,2 addition is the kinetic product. It's favored at low temperatures. So addition here is favored at low temperatures. And addition here, the 1,4 addition product is favored at higher temperatures. And so I can't really, tell you, oh, this is cold, that's hot, and expect you to get it right on an exam. Mostly on the practice, I just want you to think about it. But I could say on an exam, here's the addition of HBr to a diene. You get this ratio of products at a given temperature. What do you expect to happen to the ratio of products as you increase the temperature? And your answer should be that it moves towards the thermodynamic product, or it moves towards the 1,4 addition product. That's it. Okay, so if we heat it up, we expect to get the other product as our major product relative to the previous question. So this would be our major product. And the other one will be our minor product. Just this idea that heating it up gets you more of the thermodynamic product, and cooling down gets you more of the kinetic product. HBr and peroxides, if we have just one equivalent, and just want to point out this one EQ means that there's one equivalent of HBr. And what equivalence means An equivalent is you're saying there's one molecule of HBr to every molecule of your limiting reagent. And for organic reactions, unless you're told otherwise, you can assume the organic compound is your limiting reagent. So like in these reactions at the top where equivalents are not mentioned, in those cases, we expect to have some number of organic molecules and a whole lot extra HCl molecules or HBr molecules. So we assume everything else is in excess relative to the organic compound, unless we're told otherwise. And that's usually the case. If you have your organic compound in an aqueous solution of acid or something like that, then it's going to have a lot of acid around. Acid usually the case, often the case. It's often also the case that you don't put a full equivalent. But anyway, moving on. We're looking at HBr with peroxides. So remember that HBr with peroxides is going to go through this similar mechanism. They're going to have peroxides going to break apart, give you two radicals. Those are going to do a hydrogen atom distraction with HBr. That's going to add to one of your pi bonds to give you the more stable radical. So our question is, what does the more stable radical look like after we add Br to one of the pi bonds? So if we add bromine to one of the pi bonds, the radical should go here. But of course, there are two resonance structures, just like we saw before. And those two resonance structures we could imagine hydrogen adding to either of those to give these two products. And again, we're back to this idea of hot versus cold. Under hot conditions, we're going to expect to favor the 1,4 addition product. So under hot conditions, this will be our major product. The other will be our minor product. So we're just going to put our major product now. Sort of run out of room. But your minor product would be the other one, would be the 1,2 addition product. And if we add one equivalent of Br2, that goes through a slightly different mechanism. That goes through that bromonium ion intermediate. So you add Br2 to a pi bond. Just a quick reminder about that. This one had a lot of arrows in the same step. So this forms the bromonium ion intermediate. And then there are two options here. One is that bromide attacks. The other is we don't consider this to be a bromonium ion intermediate, but instead we consider it to be a carbocation that is allylic. So it's a very stable carbocation. And so to the extent it exists like this and not like a normal bromonium ion, now you have the possibility of resonance. So you have the possibility for 1,4 addition in addition to 1,2 addition. And so here we think of the bromonium ion as existing more or less in solution, but it is easily opened up. This ring is easily opened up by either direct attack from bromide, which is what we see in a normal bromination of a double bond, or we can do what's called an SN2 prime mechanism. So let me get rid of that circle real quick. There it goes. So let's look at what that'll look like. So we'll take this. So for 1,2 addition, we just attack the bromonium ion as usual. Remember that we're attacking the more substituted carbon here because this one is bearing some of this positive charge. Whenever you have a bromonium ion, if one carbon atom is less substituted, the other is more substituted, you actually have a little bit of a delta plus on this carbon relative to this carbon. That's going to attract your nucleophile. Anyway, long story short, this is the product from that reaction. Alternatively, we can have that SN2 prime like mechanism. So we'll go ahead and get rid of this for now because we're just thinking about that. And so here we have bromide again attacking. But if instead of attacking this carbon, the second carbon of this molecule, what did I do wrong here? I did something wrong. I added too many carbon atoms. That's what I did wrong. Always check your work. Like, you're going to make mistakes. It's not a big deal, but just make sure you're checking at every step. Is this right? Is this right? Is this right? Because losing or adding carbon atoms is a really, really common way to mess up a question. Anyway, we can attack at this carbon. Why would we do that? Well, if we attack at this carbon atom and the electrons go in this direction, now we have satisfied the valence shell of this carbon atom with the pi electrons and allowed this bond to break. And so here we've added bromine to this side, and we have bromine at this position. So that's how we get 1, 2, and 1, 4 addition. This is our 1, 2. This is our 1, 4. The question gave us the hot condition, so we're expecting to get more of the 1, 4 product and less of the 1, 2 product. And again, this whole hot versus cold thing, it's very ambiguous the way it's written on this worksheet, but that's okay. We're just thinking about it. If it's hotter, you're going to go more towards the 1, 4 addition product. If it's colder, you're going to go more towards the 1, 2 addition product. All right, moving on. So for number 6 on the worksheet, use the resonance structures and sketch a reaction coordinate diagram to explain the energetic differences between the kinetic and thermodynamic products. And here we'll just think about 1,3-butadiene. And so if we have 1,3-butadiene, it has some energy. It's going to go through some activation. And here we're thinking about adding, let's say, HBr. So there's some activation energy to get to the carbocation intermediate and bromide as a byproduct. And then we know if we go hot, we can get over a larger activation energy and get to a lower energy product. If we keep it cold, we don't have as much energy to get over that activation barrier. And the product, it turns out, is also higher energy than the thermodynamic product. So this is our kinetic product, which is obtained from cold conditions. This is our thermodynamic product. The thermodynamic product in this case looks like this. The kinetic product in this case where am I? I'm looking for blue. There we go. The kinetic product in this case looks like this. So 1, 2 addition versus 1, 4 addition. Okay, explain the energetic differences between the kinetic and thermodynamic products. So this is actually a little tricky. If you look at the products, we can rationalize the red product being the thermodynamic product over the blue product because the double bond is more substituted. So in terms of that double bond degree of substitution, this is the red one is the lower energy product by far. So, okay, that explains why the products are different in energy. The thermodynamic product is lower in energy because it has a more substituted alkene. It's a di-substituted alkene versus this a mono-substituted alkene. But why are the activation energies different? And so if we think about the activation energy leading to the blue product, the transition state. So here I'm drawing the transition state for the blue product. We had so we're talking about the addition of Br to this carbocation. So there's going to be some Br bond forming in this reaction. That's for the blue product. For the red product, we know that we're going to have something like this. Some amount of Br bond forming to the 4 position. Okay, that's fine. We consider that this is a resonance structure. If we have partial bond forming, then we have partial bond breaking. So there's partial bond breaking here. And there's a partial positive charge here and a partial negative charge here. Versus the red case, where we have a partial positive charge here and a partial negative charge here. Let me get all my bonds sort of in there. Okay. All right. So this is what the transition states look like more or less. Not sure why these became blue, so I'm going to try to fix that. It became, well, this became blue. There we go. Okay. And so what I'm trying to point out here is just this idea that for the kinetic product, you're building up positive charge on a secondary carbon. Whereas for the thermodynamic product, you're building up charge on the primary carbon. So the thermodynamic product is harder to get to its transition state. It has to form something that looks more like a primary carbocation. Whereas for the 1,2 addition product, it has to form something that looks more like the secondary carbocation. And that is more stable. All right, moving on. Number 7, write a reaction, starting materials, reagents, and products for a simple Diels-Alder cycloaddition reaction. So the simplest one that we think about is butadiene and ethylene. And we know that this doesn't quite work. We know we need something a little bit more reactive than ethylene for this to go. But to keep it as simple as possible, that's what I'm going to do. If we want to make it a little more complicated, which we can do in a minute, then we can do that in a minute. Okay, so starting materials, reagents, and products, we don't need any reagents. And our product is going to be a cyclohexene ring every time. And in this case, it's only a cyclohexene ring because there are no other atoms here. So the diene is here. The dienophile is here. So would the reaction rate be increased or decreased by electron withdrawing, electron donating groups, the diene and the dienophile? So for the diene and the dienophile, we typically want electron donating groups on the diene and electron withdrawing groups on the dienophile. That will help to increase the rate for a normal electron demand Diels-Alder reaction, which is what we're considering in this course. Okay, we'll see a lot more Diels-Alder, so I'm just going to move past this and go to the next question. Okay, so question number 8, you're asked to rank the dienes below from least reactive to most reactive for Diels-Alder reactions, identifying any compounds that would have similar reactivity. So there's a lot here, of course. This is really just a chance to think. An exam question wouldn't look like this. You would need to be simplified and be more targeted. But let's get into it. So we start off by thinking about butadiene. Everything that I think about for Diels-Alder, for dienes, I start off with butadiene as my starting point. So, and then I ask myself, for a given diene, is it more reactive? So more reactive or less reactive? So we have this continuum, and then we just sort of place them. We know that cyclopentadiene is a very reactive diene. We've seen that a lot. Remember that it needs to be in the S-cis conformation for a Diels-Alder reaction to occur. So up here, I drew my double bonds, my conjugated dienes, which is just fine. But in order for the Diels-Alder reaction to actually occur, if we look at this mechanism, we have to draw the diene in the S-cis conformation, not in the S-trans. It doesn't matter if you go clockwise or counterclockwise here, because it's a concerted mechanism. It doesn't really go in either direction. But yeah, so that's our mechanism. And in order for that to occur, our diene must adopt this S-cis conformation. This is S-cis, not S-trans. So it's okay to draw it as S-trans, but when you're writing your mechanism, you need to put it in the S-cis conformation. When you're ranking reactivity, you need to consider its ability to adopt the S-cis conformation. And of course, for cyclopentadiene, it is always in an S-cis conformation because there's no way for that to rotate around. Okay, so we talked about cyclopentadiene. What about these other ones? Well, this one here has no way of adopting an S-cis conformation. So this is just not reactive at all. Similarly, this 1,4-diene is not a conjugated diene at all. It has these sp3 hybridized carbons in between, so that's not going to react at all for Diels-Alder. So we've done this one, we've done this one, this one. Next, we have cyclohexadiene. I'm going to rate that really similarly to cyclopentadiene. It's a double bond that's always in an S-cis conformation. It's a little bit slower than cyclopentadiene, but it's, I would say, negligible. We already did butadiene. Okay, so let's look at this one. So this next one, we have to put it in the S-cis conformation. So if we think about the equilibrium between this and this, we ask the question, which side of the equilibrium is favored? And so this has our our two methyl groups attached, and this has our two methyl groups attached. And you can see that things are starting to get closer in space as we put it in the S-cis conformation. That's always true. Whenever you have butadiene and you consider S-cis versus S-trans, there's some interaction of these hydrogen atoms right here that's going to make that less stable. So actually, for butadiene, we know that we slightly favor the S-trans conformation. Even though we need the S-cis conformation for our reactions, the molecule itself prefers to be in the S-trans conformation most of the time, or more of the time. But enough of the S-cis conformation exists at room temperature that we can use it. As we go to bulkier and bulkier groups, placed in such a fashion that they get closer together when we go to the S-cis conformation, that's going to decrease the probability of forming the S-cis conformation. So this one's even less likely to form the S-cis conformation and more likely to be in the S-trans conformation, making it slower to react. And that's the end takeaway, is this is going to be slower to react because less of the molecule at any given time is going to be in the appropriate S-cis conformation. And so we're saying those two are the same. These two are different. Those two are about the same. And we're just saying about. So what about this one? Well, similar problem to the one above. I would rank it very similar to the one above, maybe a little bit faster. Maybe not. So approximately the same. That's really all you can say is approximate. Here, what about this one? Well, here, if we rotate the molecule, the two methyl groups are pointed away from the middle. They're no longer interacting. So the interaction here is very similar to the interaction of butadiene. So I would rank that one to be about the same as butadiene. So really the stereochemistry here mattered. Going from a case where these two double bonds had the double bond and the methyl group cis to each other versus the case where the double bond had the double bond and the methyl group trans to each other, that, after you consider the rotation, had a big effect on what the steric interactions would look like. What if you have one in each direction? So this one here is running out of room. And this is where you have to be careful with your rotations. And so now we have one sort of pointing in on the S-cis conformation and one pointing out. So that one pointing in is going to interact more with this hydrogen atom than a plain old hydrogen atom would, because that carbon atom that's pointing in has its own hydrogen atoms attached. And so things are going to get crowded pretty quickly. And so that's going to be slower to react than just having a hydrogen atom there. But not as slow to react as putting two methyl groups together. And so it's going to be somewhere in between these two. And so we're just thinking about it logically. You know, what happens as we do this? How does it affect the rate of the reaction, the probability that it will adopt the S-cis conformation? This is more likely to happen than this one forming the S-cis conformation, where you have to bring two methyl groups closer together. What about this one? We talked about this in class. It's sort of a weird one, or rather a counterintuitive result. If we consider the equilibrium between the S-cis and S-trans conformations of butadiene, and we look at what would happen if we added a methyl group, there we go. So if we look at this versus this, we're comparing these two. And in this second case, in this second case, we have an extra methyl group here and here, and an extra methyl group here and here. And so remember that for butadiene, the reason why the S-trans conformation is favored over the S-cis is because by putting the S-cis conformation, you start to have interaction of these hydrogen atoms. Well, as we put these methyl groups here, there's no getting around it. No matter which conformation you're in, you have interaction of those hydrogen atoms. And so, although it raises the energy of the the S-trans conformation, or rather by raising the energy of the S-trans conformation, what we've done is made them approximately equal. And so the relative amounts, the relative ratio of S-cis to S-trans is going up. In this particular alkene, S-cis has gone, the percentage of molecules that are in the S-cis conformation versus S-trans has gone up relative to just butadiene. Because we raise the energy of this side, making it more likely that they'll be equivalent over here. Here on the left, this side is lower energy. Here on the right, both sides are approximately equal energy. Or that equilibrium is related to the energy of those two. And so this one's going to be a little bit faster than butadiene. Finally, this one with those two giant terp-butyl groups, I'm going to rank that somewhere over here. Because remember, we ran into all these problems where we start putting these together. Well, if you add another group to this, then you're going to have more problems. So it'll be somewhere over here. Maybe it'll react very slowly, maybe not at all. And then there's some that can't react at all. Whereas if you put actually, no, I'm sorry, I misspoke. The terp-butyl groups are in a different spot, which is what I was about to talk about. So let's talk about that. So here we're looking at this molecule here and comparing it with this molecule above it. So the molecule above it, when we put it in the S-cis conformation, looks like this. Whereas the other molecule so we're comparing this one with, and you can start to see the problem here. As we put those two terp-butyl groups next to each other, they're going to really want to get away from each other. It's going to drive this equilibrium very much to the S-trans conformation. Long story short, this big thing ends up over here. All right. Yeah, we'll just move on past that. So hopefully that was understandable. And we'll move on to the next question. Okay, so here you're asked to rank the dienophiles from least reactive to most reactive for a Diels-Alder reaction, identify any compounds that have similar reactivity, indicate no Diels-Alder by crossing out dienes and dienophiles where appropriate. So I didn't cross them out up here. But what we were saying up here was these wouldn't react. This probably wouldn't react. All right, so anyway, doing this for the dienophiles below. This probably should just say dienes or dienophiles, not dienes, because there are no dienes down here. Oh, that's not true. There's a diene down there. But we're considering it as a dienophile, so we need to leave that that way. Let me just update the worksheet real quick. Okay, come on. You got this. Okay, so we're considering these as dienophiles. So wait, isn't this a diene? It is a diene, but we're considering it as a dienophile. So we talked about in class how cyclopentadiene is a really reactive diene, so reactive that it will react with itself in a Diels-Alder reaction. So one equivalent of, or one molecule of cyclopentadiene will act as the diene, the other will act as a dienophile, and you'll get something like this. Always forming that cyclohexene ring, nothing to really think about there. And then where's that new bond going to be? Well, we're going to have a new bond. And this is where numbering can help. I'm just going to arbitrarily call this 1, 2, 3, 4, because I like to think of my diene as having 4 carbon atoms. So over here, this is carbon 1, 2, 3, 4. You can see that this is where we form the new pi bond. between carbons 2 and 3. Okay, so now let's just read our arrows. We're going to call this 6, 7, 8, 9, 10. How you number it doesn't matter. We're not doing it for naming purposes. We're just doing this for keeping track. Okay, so what's missing? Well, and which carbons are which? Well, carbon 1, according to these arrows, bonded to carbon 6. So carbon 1 bonded to carbon 6. This must be carbon 6. This must be carbon 7. There should also be a bond to carbon 5 between carbons 1 and 4. This is where we get those bicyclic structures. That's our carbon 5. So carbon 5 is right there. And then where are the rest of them? Well, the rest of the atoms are going to be our cyclopentane ring that is over here. So 6, 7, 8, 9, 10. And again, read your arrows. The arrow did not do anything. Arrows did not do anything with this bond between this pi bond between 9 and 8. So this is your product. This is the adduct between two molecules of cyclopentadiene. And at the end, always check your work. Ask the question, do I have the right number of carbon atoms? Here are 5 carbon atoms for this one, and here are 5 carbon atoms for this one. Okay, so that is a diene. What makes dienes, I'm sorry, a dienophile and a diene, or considering as a dienophile, what makes dienophiles more or less reactive? Well, we saw earlier that electron withdrawing groups make our dienophiles more reactive. And so we don't have that here. And so I'm going to say, relatively speaking, this is going to be not such a great dienophile. So less reactive, more reactive continuum. Less reactive side would be this, roughly equivalent to any other regular alkene with no electron withdrawing groups. Excuse me. Okay. So let's do the next one. We have this dienophile. And here we have an electron withdrawing group on the molecule. So we have this giving us a partial positive charge on this carbon atom and a partial negative charge on oxygen. And so if we think about resonance structures here, so you can think about the positive charge as pulling electron density away from the double bond, making it more reactive. Another way you can think about it is by considering resonance structures in this case. And so if we imagine our electrons doing this, then we end up with a positive charge here and a negative charge here. So we put positive charge onto the one of the atoms of the alkene. So that's another way of thinking about there being a beneficial effect. Now, I just want to be really clear. This partial positive is on the carbonyl carbon, not on the other carbon. There you go. Just wanted to be really clear about that. Okay, so that's one way to think about it. We know we put an electron withdrawing group on there, so we know that's going to make it more reactive. So we put this dienophile somewhere over here. I'm going to skip ahead to this one. And for this, we'd expect to get a similar result. Here we have a double bond. We have a carbonyl carbon adjacent to the double bond, and you're going to get a similar result. So those two should be about the same. A maleic anhydride, that's one of our more reactive or most reactive dienophiles that we've seen. And the reason, well, 2 reasons why it's so reactive. One is that it has 2 carbonyls instead of 1 directly attached to the double bond. So that's going to have 2 partial positive charges. Also, there's an extra electronegative atom in the molecule, pulling electron density away from this carbon atom, making it more positively charged, pulling more electron density out of the double bond. So remember, electron density is spread out over the molecule. More electronegative atoms are going to pull it towards themselves. That's going to leave behind a partial positive charge wherever the electrons aren't. Okay, so we just have these 2 left to deal with. So for these, it's helpful to think about them in their fully drawn out structure. So this is C triple bond N versus C triple bond N. So that's what a nitrile group or cyno group looks like. And so if we consider this here, in these cases where we knew we were making the molecule more reactive, these are carbons 1 and 2 of the dienophile, and the carbonyl carbon is 1 away. So if this is carbon 1 and 2, this is the carbon that's 1 away. If this is carbon 1 and 2, this is the carbon that's 1 away. Okay. That being said, where are my formal charge or my partial charges? Where are my polar bonds in this molecule? Well, the carbon-nitrogen bond is polar. It's going to put a partial negative on the nitrogen and a partial positive on the carbon. This puts a partial negative on the nitrogen and a partial positive on the carbon. Here, the partial positive charge is right next to the alkene. Here, the partial positive charge is separated from the alkene by an sp3 hybridized carbon. Therefore, we can't consider resonance in this second case. So this case over here, we're not going to consider resonance. This one we will. And so for that, we expect the cyano group or the nitrile group that is directly attached to the double bond to be more reactive, and the one that is further away to be less reactive, but still more reactive than a normal alkene. All right. We're good. Next question. All right. The next question on the, oops, didn't do that. The next question on the worksheet is to predict the Diels-Alder product for each diene and dienophile pair below until the process becomes easy for you. Now, I don't expect you to go through every possible pair of dienes and dienophiles. So you have 1 times, so 11 here, 11, 11, 11, 11, 11, 11, 11, 11. So lots and lots of possible combinations that you could put together here. So, do it until you feel like you don't need to do it anymore. And that's really a matter of judgment. So looking at the first one in each case, we have butadiene. I'm drawing it in the S-cis conformation. Here I have a dienophile, not a particularly great dienophile, but we're not asked to talk about the rate of the reaction. We're just asked to predict what the product might be. And so here, here, here. Always start by drawing a cyclohexene ring. Don't think too much about it. In this case, here's our new carbon atoms that we've added, and they're going to be 2 methyl groups attached. Now, with the Diels-Alder reaction, we need to pay attention to stereochemistry. Whenever you have a cyclohexene ring, you have the option of putting these 2 groups on the same face of the ring, on opposite faces of the ring, or on the same face but on the other side. Now, in this case, this particular case, whether you put them on wedges or dashes doesn't matter because those 2 are both meso. They're not chiral compounds, so it doesn't matter which one of those you choose to draw wedges or dashes. Opposite sides, though, would be incorrect. To put the methyl groups on opposite sides of the ring would be incorrect because the 2 methyl groups are on the same face of the double bond when this new single bond forms. That means they have to be on the same face of this ring when the new single bond forms. New single bonds form, excuse me, new single bonds form. Talking about the formation of these bonds, can't see that. Talking about the formation of these bonds here. When those 2 bonds form, these methyl groups are on the same face of the double bond, therefore they'll be on the same face of the ring. If we think about a ring as a planar structure, which we know doesn't really exist like that, but if we think about it that way, so you have your ring that's formed, and your methyl groups are going to be on the same face of the ring. And your hydrogen atoms will be on the other face. Because this right here, that I've kind of sketched in as your edge of the cyclohexene ring, was previously this double bond. If it was a trans double bond, then one would be up and the other would be down. Okay, so that's one product from the first 2. What if we combine butadiene with the second one? Well, butadiene plus the second one gets us this cyclohexene ring. And then here are our 2 carbon atoms that made up this right here. And so let me try that a different way. We'll call this carbons 1. Nope, we've been calling the other ones 1 through 4. So these are 1, 2, 3, 4, 1, 2, 3, 4. And we'll call this 5 and 6. So here are 5 and 6. 5 and 6 each have 2 methyl groups attached. So it doesn't matter. You don't need to show wedges and dashes because it's all the same. They're going to be 2 methyl groups on the same face and 2 methyl groups on the other face. All right. What if you have the trans situation here? So if we're talking about this being carbons 5 and 6, well, in that case, we form our ring. One methyl group will be up, the other will be down for the same reason that both were up here. Now, this is a chiral compound, so it's going to be a racemic mixture. We get equal amounts of both enantiomers for this one. And so that's really it. You just kind of want to keep working through these until they're easy for you. Now let's do one of the harder ones where we have some electron withdrawing groups, and we can think about secondary orbital overlap. So let's do a really common Diels-Alder reaction between cyclopentadiene and maleic anhydride. Where did it go? 5, 6, 7, 8. I'm just numbering the carbon atoms. Okay, so if this is my carbon 1, 2, 3, 4, 5, and then these are my, this is my maleic anhydride. This is my carbons. Oops, I numbered that 5, didn't I? Because this starting material here, because the diene had more carbon atoms in it, I need to change my numbering system. Okay, so carbon 6 and 7, 8 and 9. Okay. And so we're going to form our new bond. This is where, showing your mechanism can be really helpful to keep track of where bonds form and where they break. So just reading my arrows, first off, I know I form a cyclohexene ring because it was a Diels-Alder reaction. I know my double bond is going to be between carbons 2 and 3, and this as written. I know these are carbons 6 and 7. Anytime you react with cyclopentadiene to form a Diels-Alder adduct, you're going to have that bridge in the middle. That's going to be carbon 5 as numbered here. Carbon 6 and 7, if I just read my arrows, I didn't break any bonds over here other than the pi bond. So that's my product. Now there's some stereochemistry here. So if we think about this product, we know that both of these carbon atoms had to be added to the same face of the cyclopentadiene ring. But do they prefer to add to the top face, the bottom face, or no strong preference? And this is where that idea of secondary orbital overlap comes in. And I think it's probably going to be easier for me to show you the picture from the text. So here is your diene. Here's your dienophile. The dienophile is going to line up so that the electron withdrawing groups, where that partial positive charge is, where you have that p orbital that wants electron density, those are right under these carbon atoms, these p orbitals that have electron density. So this is where your bond's forming, where the pink lines are. But back here at these two carbon atoms, what we numbered carbons 2 and 3, those have secondary orbital overlap with these carbon atoms, the two carbonyl carbon atoms. And that helps to stabilize the transition state for the endo product and relative to the exo product. And the exo product, which is what happens if you put the endo, you're going to put the dienophile under, you're going to put the electron withdrawing groups under the diene. In the exo product, you're going to put them away from the diene. And so in the exo product, which is not formed in this case, you end up with maleic anhydride being, or the part that looks like maleic anhydride, being closer to the 1 carbon bridge. In the case of the endo product, maleic anhydride is closer to the 2 carbon bridge. And that'll always be true for cyclopentadiene. Endo is putting it closer to the 2 carbon bridge. Exo is putting it closer to the 1 carbon bridge. Endo is preferred. It's called the Alder-Endo rule. We also learned about the cube method. Let me pull that up. So we talked a bit about this in class. I got this from the website up here in the file name. And so this idea of secondary orbital overlap being favored, so the dashed lines are the new bonds. The secondary orbital overlap is the interaction of C and D with the pi electrons in these pi bonds. Whereas if we put C and D away from this diene, then we find that C and D do not interact with these electrons in these pi bonds. And that's where we talked about the cube method. The cube method is sort of a trick for keeping track of where all your different groups will be located at the end. And so let's go ahead and just put that down there for now. And so this is something you're going to have to practice for it to be useful. But I think it's worth it. It's definitely worth it if you're going to do anything with Diels-Alder, which you will in this class. Okay, so looking at this example here, if we were to use the cube method, we're going to draw the top of a cube, and then our extra carbon looks like this. That's our carbon 5. This is 1, 2, 3, 4. Okay, that's our top of our cube. The bottom of your cube, so the diene is the top of the cube. The bottom of the cube is your dienophile. And you're going to orient your dienophile such that the electron withdrawing groups go under the bottom of the cube. And this is where you're ready to use the cube method instead of trying to draw it. Now I made a mistake there. So think about how you draw a cube. You would draw a cube something like this. Something like that. And your dienophile ends up being right here. That's your dienophile, and these end up being your electron withdrawing groups. Let me get rid of all that and draw it in for real. So this is our new bond that's going to form. This is our new bond that's going to form. This is our 6-7 bond of our dienophile. This is our carbonyl carbon. This is our carbonyl carbon. This is our oxygen. Shouldn't be bent because it's a very planar molecule there. And these are our carbonyl carbons. And so the cube method is not a way we would typically draw organic molecules. It's a trick for visualizing the products of a Diels-Alder reaction. So the secondary orbital overlap happens back here with these two units, and then the primary bond formation happens up here. So that if we consider what it looks like after the reaction, we're going to form those new bonds. This double bond is moving to between carbons 2 and 3. This single bond is still there. That's what our product looks like. And so you can see in this representation that the maleic anhydride part, the anhydride part of this molecule, is now closer in space to the pi bond, the two-membered or the two-carbon bridge, than it is to the one-carbon bridge. Another thing to remember is that there are hydrogen atoms here, just like there are hydrogen atoms here. And so that makes this a chiral carbon and this a chiral carbon. Each of those has bonds to 4 different groups. And so they're chiral carbons. You're fixing the stereochemistry in your product. All right. And so you can mix and match, do different combinations. There's also this document available, which is just Diels-Alder endo products examples. And so this just gives you different combinations of dienes and dienophiles, and then the answer as well. So you can work through these on your own on the left and then check your work against these. W just means any generic electron withdrawing group. It could be a carbonyl, it could be a cyano group, it could be whatever you like as far as an electron withdrawing group. Okay. Let's do the next one. Okay, number 11 is actually asking us to do what we just did up here. Draw and label the endo and exo products for the reaction below. Why is the endo product energetically favored? So the endo product, I guess it's not exactly what we did. The endo product, I'll just show it from the text, is the one that we were drawing, and the exo product is the one that's not formed, where the anhydride is closer to the one carbon bridge. Use curved arrows to show movement of electrons in the retro Diels-Alder reaction shown below. Draw the retro Diels-Alder product obtained. Check your product at the bottom of page 468 in the text. And so here, when we're going to do a retro Diels-Alder reaction, we want to first identify our cyclohexene ring. So we could call this our cyclohexene ring, or we could call this our cyclohexene ring. Okay. Which of those could have formed from a Diels-Alder addition, a Diels-Alder reaction? Actually, that's not a cyclohexene ring. Neither of those are cyclohexene rings. Those are cyclopentene rings. We need the cyclohexene ring. There we go. Let's get a little weird for a minute there. Cyclohexene ring, 6 carbons. Okay, that's the only cyclohexene ring there. So we call this carbon 1, 2, 3, 4, 5, 6 for our cyclohexene ring. Now the numbering is going to be a little different than we've been using before, but that's fine. And so if we think about our cyclohexene ring, so I'm thinking about it in the forward direction right now, but not retro Diels-Alder. So all I'm doing is redrawing the molecule on the at the start of this problem. Okay, if we think about what this might have come from, then we can say, okay, this must have been that, this must have been that, and then this must have been that. And I guess I didn't really think about it forward, I thought about it backwards, but that's what happened. Let's see that again. If we think about, remember, this is our cyclohexene ring, so we're going backwards. We reform the double bond, reform our single bond, reform our double bond, and reform this double bond. And end result, you end up with these 5 carbons here. Retro Diels-Alders can be a little bit hard to see. Plus the other 5 carbon atoms. That is not a 5-membered ring. Like so. So this is just the Diels-Alder addict form from cyclopentadiene reacting with itself. Okay, for the last problem on the worksheet, use curved arrow notation to show the polymerization of butadiene using a generic initiator. Draw bond line formulas for cis polybutadiene and trans polybutadiene, and you can check your work at the top of page 470 of the text. So we're talking about taking butadiene, and we're going to form cis polybutadiene and trans polybutadiene. And so probably just start with trans. Trans polybutadiene will have a trans double bond. The N indicates that you have some number of repeat units. That's this little N right here. The parentheses indicates that the stuff in the parentheses, these atoms, repeat over and over again. So if we're calling this carbon 1, carbon 2, carbon 3, carbon 4, we're saying that the next carbon 4, this carbon 4 bonds to another carbon 1, which is bonded to a different carbon 2, carbon 3, and carbon 4, which is then bonded to a different carbon 1, all in a nice long chain. So if N equals 3, then you'd have something that looks like this. We're just imagining right now what if N equals 3. So we have to be careful here. 4 carbon atoms. 1, 2, 3, 4 carbon atoms. What am I doing wrong? 1, 2, 3, 4 carbon atoms. 1, 2, 3, 4 carbon atoms. I'll circle every other one here. 1, 2, 3, 4. That's right. And then because we're talking about polymers, you end up with this weird situation where you have what look like methyl groups at the end of the molecule. And so with polymerizations, in many cases, we don't know the end groups for our polymers, or we know what some of the end groups are, but we also know that many of the end groups in our mixture are different. And so for that reason, in polymers, and only for polymers, that what looks like a methyl group there at the very end actually just means some unknown species. That's what it means for polymers. Now, if you actually draw it out like this, where you show all the bonds, that would be confusing because you don't have the parentheses. So you can do something like X and Y here, just indicating that whatever your initiator was, whatever your terminating group was, they're going to be at those locations. Okay, so this is trans polybutadiene, and then cis polybutadiene will have a cis double bond. 1, 2, 3, 4, and number of times. Use curved arrow notation to show the polymerization of butadiene with a generic initiator. And so that's shown in the text as just initiator. We can imagine it as a radical, as an anion, as a cation. It's going to be some reactive species, but for now, let's just pretend it's a radical. What does that look like? Well, we're going to form our radical intermediate. And here we do know what's at this end of the molecule. IN just stands for some generic initiator here. And here we have this radical. Now we want to form, in this case, I'm thinking about trans polybutadiene. And so we'll need to do a bond rotation, and we'll need to, actually, we don't need to do a bond rotation here. We need to show the resonance structure, or just have, you can show the resonance structure, or you could do it another way. Actually, let's just do it the other way because I think that'd be informative. So you have this radical that forms as an intermediate. And then you have another molecule of butadiene because we're considering polymerization. There's a lot of butadiene coming together to form these long chains of molecules. And so how do we get something that looks like this from this situation? In order to do that, we need to make a bond between carbon 4 and the next carbon 1 of butadiene. Our radical is here on carbon 2. So we'll do this. To give us our trans butadiene. 1, 2, 3, 4, 1, 2, 3, 4, trans butadiene, and a radical. And that goes on and on and on again and again and again. Did I skip ahead? I did skip ahead. My mistake. So what I did was I drew the resonance structure. You can know this is one resonance structure. The other resonance structure that you could draw would have the radical on the end carbon. So here are your first 4 carbons of butadiene from butadiene. Here are your second 4 carbons from butadiene, and so on and so on. Okay, so that's how we form the trans product. To form the cis product, you just show this molecule in the cis conformation, or you can show the resonance structure that puts the double bond in the middle and show that as an intermediate. So what I'm saying here is to form the S-cis product, or rather the cis polybutadiene, then we could have the same first step. Our initiator attacks, you form this radical. But for now, I'm just going to consider this conformation. And just to make it easier on myself, I'm going to consider the resonance structure that forms, because it does exist as a hybrid. First, you have to change your conformation, then draw your resonance structures, because remember, for resonance structures, we're not allowed to switch bond positions. We can only change the electrons, the pi electrons of the lone pairs. And so you can see this forms a cis double bond, which can then polymerize to form cis polybutadiene. Okay, and then your work, it's talking about checking that in the text. Yeah, so this is an example of that. You have cis and trans polybutadiene. Okay. And there's actually one other form of polybutadiene that you can get where you have these double bonds sort of dangling from the long chain. But this is just an example of if you were to form this polymer, propose a mechanism for it. And remember that polymers are used everywhere in our daily life, so their polymerization is really important. For example, rubber. Rubber is incredibly important. Latex is incredibly important for technologies. Okie doke. I think that's it for this worksheet. I will see you next time.